All right, I think I should go here. So howdy, everyone. Okay, great. So yeah, thanks for the kind introduction. I'm Marcus. I'm a professor at Texas A&M. I'm a researcher. I'm a scientist. I'm an academic. And a good thing about being an academic is that we are free to dream. We are free to try to forecast the future. We are free to try, to have visions about how the future will be. And that's what I have been doing the last years, trying to predict and forecast what are the threats that you are going to face in the future. And that's what I'm going to talk to you right now, right? It would be good if it works. It does not. I tried. Okay, now it works. Okay, so I'm going to try to talk a little bit about how is the future. So more specifically, how can we create malware using all these GPT and these kind of models, right? It works only when he wants to work. Okay, pretty good. So I think that this point, it's needless to say about what's the importance of all these GPT, LLM models, all these kind of things that are happening right now. But it's important to talk about the security of all these models, right? Because we, security paranoid people, whenever we see a new technology, the first thing that we think is, okay, what might go wrong, right? And I have been working the last years on these kind of things. And when I say the last years, it's really in the last years, as you can see here by the news, because since the inception, the emergence of these models, people have been wondering, okay, how attackers can abuse this kind of model. People initially thought about like, okay, maybe we can use this to vulnerability exploitations. And I personally thought about, okay, what if attackers use these models to write malware at scale? And that's what I would like to talk about today. Whenever I talk about that, something that people ask me is about, okay, you're talking about these malware generation things, but is this a real thing? Is this something that I should be concerned about? Or aren't you dreaming too much in the future? Because, we academics are not very known for practicality, right? But in this case, the reality itself answers our question. Come on, reality, come here. Basically, that is, if you live in the underground forums like me, basically it's very easy to find some attackers bragging about their capabilities of, creating malware using ChatGPT. You are going to find it there, right? So yes, it's possible, it's true. I think the question at this point is, okay, to which extent is this possible? How many samples they are going to create? How scalable is this? This is the kind of question that we have at this point. And that's what I'm trying to answer here right now. So basically, how do I think that attackers are going to use these kind of things? What's my vision for this future possible use of this technology? And my vision is that, the clicker doesn't help me at all. My vision is that the attackers are going to use this as part of exploit kits. If you don't know what exploit kits are, basically what you have to understand is that there are basically two tiers of attackers out there. The ones who are more skilled that provides code to the other ones, the script kit is to attack anyone out there. So basically they use this kind of tool. Somebody creates a tool like this that basically whenever you click in a checkbox, you enable this functionality in your malware. So even if you don't know how to program really well, you can just go there, select some checkboxes, and basically, well, you get your malware done. Put the IP address of the victim in there, and basically everything is done. So basically, this is how things work in the underground world. What's the problem here? That from attacker's perspective, this kind of exploit kit code is very limited because you are not actually generating code. What you are doing is just enabling or disabling some features or linking to some preloaded coder over there, which limits diversity. But what if this code was generated in runtime? What if every time we click in one of these checkboxes, the code is generated by that time automatically by an LLM or GPT model? then we could have a large diversity of code, right? That in theory would cause our detection to be smaller, to decrease. And that's basically what I'm proposing here. I think this is something that the attackers might try to do in the future. But for that, we need someone more skilled to do that. And then I'm going to explain why. So if we keep moving forward, something that I need to explain is, okay, the attackers are going to do this, we have the exploit kits, but how this happens? So to explain how this happens, let's try to write some malware right there, as people think, because people are going to say, oh, now it's pretty easy. Basically, you go there, use one of these models, ask for a malware, and everything is right. But it's not that simple, because if you ever tried to use like ChatGPT and then you ask for malware, basically you get a message like this saying, nope, right? But there is something interesting here, because the first key point here is that we need to make a separation between what is the application and what is the model, right? So here, ChatGPT is an application. ChatGPT is not the model. And we should be concerned about not the application capability, but the model capabilities, right? The applications has filters, but the models might not have. Right? And then if you are serious about security, if you want to design a proper threat model, we should not only be concerned about the script kiddies using ChatGPT, we should be designing our security system for the worst case. In the worst case scenario, the attackers have access to the model with unlimited capacities, right? So if you're serious about threat model, that's what should be studying right now. What are the abilities not of an application, but of the models, right? And in this case, the model and the application are tell apart. They are separate. There is a split between that. Right now, everyone is talking about, oh, how do you jailbreak this and get access to the model? But I'm here to show something a little bit different. I'm here to tell my story. As I said, multiple years working these things. So when the way that I have to show you that it's possible to get something more from the models, and remember, attackers have no restriction in this sense. Attackers can, in the last instance, create their own, train their own large language model if it's possible. That's why we're concerned about the model, not the application. So a way that I have to show is to show something that happened in the past. That's basically the playground. So basically, in the beginning, there was no ChatGPT when I started to play this at GPT-3, so you could have access directly to the model via the playground. And in the playground, you can do some stuff. Okay, there's always an outlier. Intrusion detection, in real time. And basically, in the beginning, there was even, APIs to do that. That's basically what we used to do that. So we had access directly to this model. And we could do interesting stuff. For instance, we could ask the model directly, hey, tell me something about malware. And then although right now you don't have access via ChatGPT because the chat doesn't allow, the underlying model has knowledge about these things, about malware, what is malware, and so on. But as you can see, this is only text. We don't want to attack anyone with words, but with code. So we need to do something better. And then all this prompt engineering came, right? And then you have to say, oh, you need to write code. This code must be in C, must be for Windows, must be here and there. Right now, you don't have to worry anything about that, because when you use like ChatGPT or Copilot, this is done implicitly by the model. When you ask something, these prompts are put there for you. But you can see that it was there since the beginning, since the inception. These things were available, and then we have been studying this for some years. But as you can see, it's possible to write some malware. The model has some knowledge. There is IOCs here and there. But it's not enough to, be something malicious. This code can cause no harm to anyone, right? Although the model knows something about the malware. So it's not that easy, right? That's the message. It's not as simple as someone might advertise to you and say, hey, go there, ask for a malware, and then you're done. You need something else. You need to instruct the model. We need to develop a way to construct the malware, right? And basically, that's why I believe that we need someone more skilled. We need an exploit kit. We need a skilled attacker to develop all these environments to create the malware. And then that's what I'd like to show, how someone would develop this environment. So basically, if we move a little bit forward, what I would like to talk first is, okay, before we try to create our own malware, let's try to investigate what are the limits of these models. What can we do with all these type of models? So what I did was pretty simple. Basically, I collected a data set of real malware samples that target a real country, thousands of samples. I traced everything, get all the functions that this malware used, and try to check, okay, does this type of model support, they allow me to create all this type of malware? And then basically what I did was getting the functions and asking the model, do you know which library this function comes from? Do you know the header that implements? Can you code this type of, give me a code using this type of function, these kind of things? And basically, this is the result that you have. There is a huge variety in support, right? Some libraries are fully supported, and many libraries, most of them in reality, are not completely supported, which means that from this data set of real malware, not all of them could be implemented using this type of model, because not all functions are supported by the model. And then here, we can have two different conclusions. You might be more, negative and then say, yeah, it's not possible. These models are not so good. There is still too much room for improvement. Or you can be more positive and say, hey, we are already amazed by this type of model. In this model are going to get even better and better because there is still room for improvement. Because what you see here, only a few libraries are completely supported, and we are already amazed by these models, right? And I'm not saying that you should not be. These models are really impressive. But what I'm saying here, we are amazed by something that is only the tip of an iceberg, because only some functions are supported, and we are already impressed and doing great stuff with that, right? So this is the scenario right now. Glass half empty, half full. Depends on how you see, right? But then you're going to ask me, okay, so I want to create a malware. A lot of things are not possible. So how do you get a malware out of this, right? Well, the message then is that not all functions are the same, right? So basically, if we understand how the functions are used, we can have something more or less like this. That's basically the prevalence in which these functions are used versus their support. So we can see that in the initial region, we have a lot of functions that are not supported. Most functions are not supported, but they are not frequent. But there is something in the upper right region right there, that is, there are some functions that are completely supported and they are frequent. Most samples use this function. So this is our technical tip of the iceberg. And then my question is, if we get only this tip of an iceberg, can we create a malware? And the answer is yes, we can create, and then that's what we are trying to do in our exploit kit. Basically, how are we going to do this? We are going to use one of the most basic computer science paradigms, that is divide and conquer. It always works, it will always work. Basically, what I'm proposing is, let's going to create small snippets of code that we restrict to use only these supported functions, and let's see what we are able to create. These snippets are what I call the building blocks, right? So basically what I did is to get a taxonomy of popular malware behaviors, and I tried to recreate all these behaviors, persistence, evasion, evidence removal, all these things, using only these supported functions. Here I use an academic taxonomy. You can use any other one, like Mitre attack framework. The result will be basically the same, because the most common behaviors can be implemented only with this tip of an iceberg, right? And better than that, basically, this is block proven, basically, because these kind of code, these snippets of codes are not malicious by themselves. They only make sense in context, right? If you ask a snippet to encrypt something, this can be part of an backup routine, or it can be part of a ransomware. The model has no way to know about that, right? If you don't give the context saying, oh, this is malicious, you are just saying, give me a function to do this encryption, it's going to give you, so nobody's going to block you. So for the attackers, it's very interesting. And nobody can block you in this sense. So the models are able, the application cannot block, it's possible to write. So basically our problems are solved, right? So basically, except the clicker problem that's not solved, but all other problems are solved. So basically, okay, let's create building blocks for everything. It should be easy, right? Well, once again, every time someone says something is easy, don't believe it. It's not that easy, never, right? But basically, we can make some adjustments. The first adjustment that we can make is, for instance, create a coherent phenomenon, a coherent code base, because since you are splitting everything in building blocks, nothing guarantees that these building blocks you'll have coherence, internal coherence. For instance, we should say, put this code in these function prototypes, because if we don't say all the code generated in main, we cannot merge all the main components because everything in main. So what we want is to, hey, follow this prototype, put each function in each code in a different function. And that's another reason why we need a exploit kit. Because every time you click in the exploit kit, what you are saying is, okay, activate this function prototype. And then the LLM goes there and fill out the code in that function prototype. So you need someone to engineer the function prototypes, because otherwise one function doesn't communicate to each other, right? So it's not that easy. We tried, it's not that easy. There are other problems. For instance, sometimes this type of code make mistakes, right? And then we'll need to fix that. So we need something, the exploit kits, to make a pass and fix all these things, because one function might be called in ANSI string, ASCII strings, and the other Unicode, and then they do not talk to each other. So we need some normalization or regularization practice. And this is another important difference. What I'm trying to do here is fully automated code generation. So I'm basically, the model generates a code, I copy this code, paste in the compiler compiles, and it works. That's what I'm trying to do. That's different than most people are using this for. Most people are using like GitHub Copilot or something like that for bootstrapping their code. So basically, hey, this is the prototype, give me something, and this person are going to change that code. So small mistakes doesn't make difference in the bootstrap task, but make all difference in the fully automation task, right? So this task is much harder than bootstrapping. And the model is really good at bootstrapping, but not so good at fully generation, right? Because the bootstrap is, once again, the tip of an iceberg. We reached a good point there, not so good point for fully automation. But we tried. And then we fixed these things, we created the scripts that fix all these errors, and we generated lots of building blocks. How does building blocks look like? Well, we pass a lot of prompts saying, hey, generate something for me. In this case, for instance, check the vendor of the processor, or if this processor is real or not. This is something that the malware does. If the processor is virtual, it's in a virtual machine, evades the analysis. If the processor is real, more likely that it's a real machine. And basically, we get some code like this. Basically, there are different ways to get this information. In the first code, you have, for instance, assembly intrinsics that are used to get this information from the registers. And the second way, it's using a Windows API. It's interesting because every time you ask these models for a response, you get a different response due to its probabilistic nature. And they are really different. They both implement the same semantics, but the way they implement is really different. One uses an assembly and the other uses like a Windows API, which creates structurally different code with the same semantics, which makes this type of model naturally a polymorphic malware generator, right? Which is pretty good for evasion, right? We can do this for multiple examples. We can do the same like for debugger identification or these kind of things. And then if you do this again, basically you can see that there is different ways to do that. The only difference in this case for this debugger identification that you're going to see is that basically the offsets of these two codes are generated. One offset is the double of the order. And the reason is that this model is able to generate code for 32-bit and 64-bit. So when you double the size of the word, you double the offset. So the model is aware of that, which, once again, it's pretty good for exploit kits generation because, well, you say, I want this function. Instead of a pre-established function, you say, I want a custom code for 32-bit or 64-bit. It generates on demand. So there is a lot of potential here from the parts that we can explore. And once we have this, all that you have to do is generate all these building blocks. Aha, right? But once again, as you can see, it's not that easy because sometimes we generate the building blocks. We ask for hundreds of building blocks of each type. Sometimes they doesn't compile, as I said, because it's wrong. Fully automation is different than bootstrapping. And if they don't compile, okay, move to the next one. And sometimes they compile, but they do not run. We tested everything in a sandbox to see if they run expected. Sometimes they compile, but they just crash because it's a null pointer or something like that. Except for my Programming 101 students that believe that compiling and running is the same thing, but it's not. So we tested. But in the end, in the real end, in the end of the day, it is possible, right? So every building block has at least one or more implementations that are fully automated, functional, and so on. And it's really fast for the attackers. As you can see, it's really, really fast. The attacker can generate millions and millions, and some of them are going to work, right? But unfortunately, none of them work in the first attempt. So in the first attempt, none of them work. You have to try multiple times each one. But okay, I have time. I try all of them and generate all these types. And what we have in the end is our malware. This is the skeleton of our malware. Basically, we have all these building blocks. We start, by fingerprinting the environment, and then we have the evasion, and then we load the shell code. In the end, we remove it. Basically, the structure of a real malware. But for each block right there, I can put 100 different implementations. So I have a exponential number of functions here. So I can create really many different malware. I can do this in parallel, or I can do this sequentially, depending on how I want to approach. In my case, I did this sequentially, because what I was trying to do is to mimic like server-side polymorphism. So every 2 minutes, I generated a new code, a new combination, and submitted to VirusTotal. And the result VirusTotal gave me was something like this. that once again we can have, see the glass half empty or half full. Because on the positive side, you can see that the right direction, many detections, right? We have two curves, and basically the first Gaussian curve that you see there are basically the detection of the samples in the first week. And the larger Gaussian curve out there are the samples detection in the second week. And this happens because the AVs update over time, and the AVs learn how to detect this type of stuff, right? So good news, the AVs are going to learn to detect this AI-generated malware. Good, right? But if you like to see on the other side, I have some bad news, because here I have thousands, 10,000 of samples. All of them are functional, all of them are achieving their goal, they are structurally different, and many of them, as you can see here in the left side, are not detected. Some of them are detected by a few, and some of them that you can barely see in the figure, but they are detected by 0 antivirus. So it's possible to detect samples that, despite malicious, were not detected by any antivirus even after the 2 weeks, right? So my whole point here is AI is not going to create anything completely new. Nothing that I'm showing here is revolutionary. This is typical malware strategies that are used out there. Every analyst is not going to know, right? What's the problem here? The long tail, right? Because the attacker can generate easily thousands or million samples. And then even though your solution detects 99.99%, there is still 0.001 that is basically corresponds to hundreds of samples that are going to break in, right? Because the attacker generates everything, try to attack you with everything, and then in the longer tail there are hundreds of examples that do basically the same stuff as the other one, but they're not detected, right? So this is the problem that I see with this AI generation stuff. It's basically massive. That's the problem, right? Okay, this is where we are right now. So I published a paper about this last year. You can find in my page and read all the details. Now I'd like to talk about something new that I never presented before. That's the research that I'm doing right now. A paper that was not published. It's out there under review. That's basically, okay, this is my story. I'm starting working these things. Many things happened in the last year. One of the things is newer models. GPT 4.0, GitHub Copilot, everything. So are these models better? And then that's basically what we did. So basically what we did was to repeat all the attacks using these newer models. So here we use GitHub Copilot. And then the message here is, yes, there was this room for improvement. The models are getting better. So you can see that for many tasks, their success in compilation rate or sandbox rates are much, much better. For some, you are going to say, no, it's worse, right? But no, what happened here is we are comparing hundreds to hundreds. But GitHub Copilot, with only 5 variations, was able to produce the same number of functional samples as the old GPT-3 So it's much better. What happens is that we keep generating until the limit, and basically we discover that the model gets more creative over time, starting generating different things. And the more different things it generates, it gets worse, less compiled, because the more variation makes it worse. But if we compare in the same fair basis, the models are getting better. And you can see this based on the first. Because before it was not possible to generate correct one the first time. But now it is. Many of them compiled and run in sandbox at the first time, which shows that the models is getting better. What's the drawback? Here, it's time, because I was talking before, okay, GitHub Copilot, fully automation. GitHub Copilot requires someone to drive the application, right? You have to open Visual Studio Code and type and so on. There is no API for Visual Studio GitHub Copilot. Well, when there is no API, we create an API, right? So basically what we did is we created a bot that type for us everything, and then basically we make a request as an API. We send a request, hey, generate this, the model automatically types everything, gets the result, compiles the malware because it's already inside the Visual Studio, and gives the malware back to us. And then if you want to watch that, there is a video, the slides will be available, you can check our bot driving GitHub Copilot. There is the drawback in time, of course, because you have to set up a VM with Visual Studio Code. It takes more time than a simple API call, but it works pretty well after you start these things. It works pretty well. Okay, we are talking about automation. So what else can we automate? What other drawbacks? Another drawback is the prompt generation, because we need to have like the prompts to create the building blocks. But what if we could eliminate the prompts? What if we could, these prompts also be generated automatically? And then I have to present you to something called GANs, the Generative Adversarial Networks. These were the state of the art in generational AI before the LLMs, right? If you don't know what is a GAN, basically the idea is very simple. Is if one neural network is good, use it too. one fighting another, right? So one is trying to generate content and the other is trying to identify content. So in this case, we are talking about malware generation. Put one neural network to try to generate malware. And then every time this is making success against the other model, is evading the detection of the other model, makes it to learn that this is the right direction. So this model gets better and better over time in creating evasive samples. And at the same time, you have a detector that you are training that gets better and better over time to identify malware samples. So they are going to reach an equilibrium. And then you are going to have the best model in creating malware and the best model in detecting malware, right? And this is pretty good. But this works in the feature space. This doesn't create the actual binary. This creates the feature that represents the binary. To say in clear words, these GANs are going to tell, put these functions in your binary, and these functions, if these functions are present, your binary is evasive. So we have a problem before called the problem space and feature space gap. That is, okay, how do I go from a function to a binary? Because if I have a binary, how can I remove a function from the binary? I am going to break the binary. It's not going to work anymore, right? But now we have LLMs, and LLMs are able to create code. So what if we couple the GANs to the LLMs? The GANs are going to suggest, hey, use this function, and the LLM is going to create the code for this function. And that's exactly what we did here. Should move. Okay, it's really slow, but it's moving. So basically, that's the idea. You input the initial prompt, and then the LLM is going to code these building blocks, generate a binary, and then you pass the binary to the GAN. And the GAN is run against an antivirus and it's going to say, hey, to evade the antivirus, you should add or remove these functions. And then we pass this thing again to the LLM. And the LLM modify, generate the same building blocks, but now instructed by the GAN, say, no, I should not use these functions because the GAN said me automatically to not do that. And then it does it again. If the binary is evasive, good for you. If it's not evasive, well, try it again and generate again and again. So basically, we are creating an iterative malware creation process that every time that you iterate this evasion, the binary becomes more and more evasive until you achieve your goals. This is something completely possible to do. Non-attackers doing this right now, but it's plausible to hypothesize that if one has an exploit kit, this can be made available to everyone. And basically, when you see the results, we applied these results to many GANs against many antivirus. And this is the average result. You can see the results are very interesting because it actually decreased detection. Once again, this is the average. So from one of the cases, we have a 14% decrease in average. That is a lot, right? For all these 10,000 samples. If we look to individual samples, we have, of course, to your right, samples that the detection increased because it was a side effect. In fact, when you added a new function, the antivirus is biased toward that function and detected it more. But for other cases, for that individual sample, it actually reduced their detection. In some of the cases, by more than 20 antivirus, which means 20 antivirus that detected that sample before the iteration is stopped detecting. So basically, we neutralize detection, right? So it varies sample by sample, but on average, it works pretty interestingly, right? That's basically what we are working right now. What else can we do? The only thing that we can do is to create malware. Not necessary. There are other things that we can do. For instance, we can have existing malware. Oops, it's moving too fast. Sometimes doesn't move. Okay. Okay, I think it gave up. Yeah, one more. Yeah. Okay, what else we can do? Basically, what we can do is we can armor existing malware. For instance, we can teach these models to obfuscate code. So if you have code, you can obfuscate this code. So basically, you can say, hey, whenever you have a string, move this to dynamically load the string with some XOR, base64 encryption, or something like that. And the model works pretty well doing this because we try to do this. And what we have is basically, we get some real malware that had this, their source code leaked, so this real source code, and then we compared. What happens if we encode these strings in comparison to, using like a traditional binary packer? And then you can see that in some cases, just encrypting the strings is more efficient than, using actually a packer to do that, right? So basically, once again, there is no novelty here. Packers are known, obfuscation are known, but now this is made at scale. Because before that, someone has to know, for instance, how to run an LLVM obfuscation compiler pass to do this, and now the person doesn't need to do anything. The person just go to a prompt and say, hey, I want to obfuscate the strings, and the model does that, right? Yeah, you can keep moving. Another one. Okay, you can keep moving, but this is not the only thing that you can do. Basically, other things that we can do is that we are in an arms race, right? So I would like to give you more defense and perspective to not leave you with this bad message that say, okay, AI is going to destroy everything, because that's not really the message that I want to deliver. That is, we are in an arms race, the attackers and defenders are playing. So far, despite all the, the crisis that we are always crying about, we are doing a reasonable job, right? So we still have more benefits from the technology than harm, right? And then what we want to do is to keep it this way, right? And basically, to do this way, we should use the same arms, because this is how we keep the things going the same pace. If the attackers has an advantage over defenders, then the game is over, right? So if they are going to use their models this way, what we have to do is basically we need to fight with the same arms. And it's possible to do that. For instance, we have some obfuscated code here, and if we use this model to do that, we can keep, deobfuscating and say to the model, hey, decode this string, convert this character, apply these things, dereference this pointer, and the models are able to do that, right? So this is pretty interesting for scaling analysis, because if on the one hand, every malware is going to be obfuscated because anyone knows how to do that, on the other side, now everyone can be a defender. Everyone can, at least we can facilitate the training because people can learn much faster how to be a defender. So this is something that we want, because now, even though, once again, there is nothing new here in the sense of the obfuscation. We have tools for obfuscation right there, but this requires specialized knowledge, right? Someone needs to know, like, what is regular expression. And right now, you don't need to do this anymore. You just go to the model and say, replace every string by something else, right? And then this works pretty well. So let's try to use this in our favor as defenders, and let's try to use this to scale our defenses, right? If we move forward a little bit more, yes, basically, what we have is, we were talking before about source code, and then one question that you might have is, okay, we were talking about source code, but what about the compiled binaries that you were talking originally? How do you detect these new exploit kits that are going to be generated? And my idea for that is that we should not look at the individual binaries, at each one of their functions or these kind of things. We should take a look at what is common between them. The same time that we detect like command and control by fingerprinting, their hand shaking or so on, not the individual payload, we should do the same here, right? So basically, we should identify what is common. There is a common skeleton. There is a common flow of information between all these malware samples, although their implementation is really different one from another, right? So if we are able to develop tools that we find this commonality between them, we are going to be able to succeed to make this detection massive, to scale our detection. And this is what I'm showing. Basically, among all the samples that are generated, there is some internal coherence, there is some similarity. I'm trying to cluster all of them, and basically if we cluster, we find some similarity. So in terms of defense, I think the next generation defense should focus on that. Overall similarity, more than the individuality of each one of them, because they will be individually different. Okay, now moving too much. Basically, okay, going towards to the end finally, because I'm talking too much, I know. But I have a final message for you that is the last one, but it's probably the most important one, that is, how do we move forward from these things? And basically, if you are following like me on Twitter or something like that, you are going to find me talking things like that about, hey, people are too much concerned on how students are going to use ChatGPT or these kind of things. And I'm not fighting the students. I'm making the students to learn how to do that. And then we need to teach, because if you want to make these tools useful, we need to teach people how to use this kind of tools, right? I know many of us ourselves need to learn how to use these tools, but beyond the learning, we need to teach these people how to make the best out of these tools. And that's what I'm trying to do. I'm trying to teach them how to do these things. You saw that it's not so easy. We need to have a structure, we need to have methodology. So let's teach the people how to best benefit from this kind of tools. And that's what I have been doing these days. So basically, I'm asking all my students in the classroom to create their own malware. You can move two more, one more, and one more again. No, okay, too much. But basically, I'm asking all students in my class to do these exercises, all their exercises to create malware and so on, using this ChatGPT. So as you can see here, they are able to do that. Here's a screenshot of a sandbox running a code written by a student. It's a fully functional malware written the same way I described it here. So if you want to be scared, okay, even a student is able to create malware this way. Imagine an attacker, right? But the good message here, we are teaching them. That's what we need to do. Teach and teach and teach. Okay, I'm a professor. You should not expect to hear anything different from me, right? Education. But that's really important, because if we don't make the best out of these tools, things are not going to work, right? And moving really, really towards the end, my final messages are like this. Yeah, so about the LLMs, you know, they are only the tip of the iceberg, right? Don't believe it too much when people say they do miracles, right? It's not right there, I have shown. It's tip of the iceberg. There's still significant room for improvement. But at the same time, don't believe some extremely skeptical people that say, no, it's not too much, it's not a revolution, because if you know how to do things, this can really help, right? And for malware creation especially, divide and conquer. Divide and conquer is beautiful. I mean, I love this paradigm. It always works, it's always going to work, right? And the same moving forward. How do we move forward? Essentially, if you want to, you should use the same arms, right? If the attackers are going to use, you have no option. You have to use it. That's game theory, right? And how do you are going to move forward? For the binary detection, develop similarity tools. This is something that we should invest on. And, of course, education. How do we best use these models, right? So basically, if you are interested in all these things I have talked about, basically, you can try yourself. All I have been talking about is available on GitHub. You can go there, get the code. Most of the samples are there, virus total detection, thousands of malware that I created. There is still everything there. You can take a look. Yeah, and that's it. Basically, thank you for your time. If you are interested in doing something, research with me. I'm always recruiting new students, partnership, research partnership, transition to practice industry, everyone that you just want to chat and hang out. I'm available. Thank you so much for your patience and for the all-clicking issues. And thank you. Questions, please. I have time. So, yeah, if you are hungry, you can also talk during the lunch. But yeah, come to talk to me. But in which sense? You mean better than the hashing, but you know, for the defenses or for the attackers? Yeah, I mean, once again, we should use the same defenses, the same arms. So if the attackers are moving fully towards this kind of automation, we should move our defenses somehow. The best way we have to generalize somehow involves some use of AI, right? So definitely, this is a direction things are going. People are already relying on AI a lot, right? But the problem that I see is that we rely on AI when we have power, but we don't rely on AI when we don't have power in the constrained devices, right? Then when we use these traditional techniques like hashing and other type of stuff. So the real challenge that I see is how to make this performance, right? Because, well, we cannot run LLM everywhere, right? So for some of these scenarios, there might be this, you know, gap between attackers and defenders. In the overall scenario, if we fight the same arms, well, I don't know if things are going to be better. If the things remain the same place, we are good. Because the attackers evolved, the defender evolved, we are still in the same place, right? And that's what we strive for in security, right? We are trying to get better to stay at the same place. That's a weird thing, but yeah. No, this is actually what, I mean, companies are doing, right? So they are training their own big machine learning models and deriving rules for that. So what you match in the end point are the rules that are derived from these big machine learning models, right? So basically, I think this approach will somehow continue. The problem that I see is, once again, scale. Like, this type of approach has limitations. So I don't know to which extent we are going to able to sustain this way. But on the other hand, also, the technology evolves in many phases. So probably we are going to be able to create smaller models that are very efficient also and performance compliant. Performance evolve, the hardware evolves. So all these things needs to move forward together, right? So that's basically what I think are going to happen. So there might be, you know, short-term modifications, but in the long term, things tend to stabilize. But of course, there is always still be some room for attacks, and that's the problem that I see. It's not the 99%, it's the 0.01%. These type of attacks will always exist. It's no inherent limitations of the model and technology and so on. But now there is a systematic way to exploit it, right? Before the attackers were exploiting it manually. Now there's an automated way, right? So you make this exploitation of this blind spot systematical. This is the real problem that I see. All the rest, you'll remain more or less the same.